much for the introduction. Actually, this is the title of the associated IEEE Sensors Letters paper, and more or less the presentation deals with the development and realization of a more sustainable resistive humidity sensor based on LIG, which is laser-induced graphene, on Chitosan. So I think the motivation behind using more sustainable materials might be quite clear, but still, the fastest growing waste stream worldwide is electronic waste, while at the same time, the number of sensors deployed increases at high pace due to ubiquitous sensing tasks and IoT. And still, humidity is one of the most relevant parameters to sense and control in a wide variety of industrial or commercial applications. So there's urgent demand for sustainable sensor solutions. So the sensor I will be presenting today is actually quite simple in design, which is an advantage as only very few materials are used. It consists of only 3 components. So you see here an interdigitated design, which is fabricated on a glass substrate. Then there's a sensing layer, which is in this case Chitosan. I will talk about this later on, what Chitosan is. And then the electrodes are fabricated from laser-induced graphene, which is derived from this Chitosan. So no additional material is added. So Chitosan is an environmentally friendly, low-cost, compatible, biodegradable, and even edible material, as it is derived from chitin, which is a natural biopolymer that can be found in the exoskeletons of shrimps and crabs. And it can contribute to the reduction of waste to employ Chitosan for the fabrication of polymers, and the Chitosan is a waste product anyways that comes from the fishing and food industry. And but still there's also a vegan alternative, so Chitosan can also be synthesized from fungi. Why is Chitosan such an attractive material for humidity sensing? You see here a simplified representation of the Chitosan molecule, and the electrical resistance of the Chitosan is influenced by the chemisorption of oxygen species on the sensor surface. So let's consider this as a Chitosan molecule with the oxygen surrounded by it, and if there is a constant voltage applied to these Chitosan molecules, then electrons are transferred from the valence band of the Chitosan to the conduction band, and they form ionic species together with the oxygen or the ozone. And so in this condition, the Chitosan has a very high resistance. But as soon as water is present, O2 is formed again and electrons are released again, which decreases the resistance, which means in principle that with increasing ambient humidity levels, the resistance of the Chitosan layer is decreasing. What I think not every one of you might be familiar with laser-induced graphene. So laser-induced graphene is a process that transforms common carbon-based materials into graphene by exposing them to high-intensity laser light. Basically, LIG can be fabricated on any carbon precursor, and Kapton is one of the most prominent materials for the fabrication of LIG. And recently, also the formation of LIG from Chitosan has gained scientific interest. So to summarize, for the LIG can be applied to various substrates. So a big bonus point is the flexibility. The fabrication of LIG is scalable as it is suitable for mass production. And it can be considered as environmentally friendly as there is no additional material added, as just the existing material is converted to graphene. For the presented sensor, we present two different sensor designs. This one is referred to as sensor 1 in the following. And here we just see a classical interdigitated structure. And between those LIG electrodes, we have the Chitosan layer. So as a very simplified equivalent circuit, you can say that the whole sensor system, if you consider it as a serial resistance, you see this as the LIG, first R, and the resistance of the Chitosan that changes with the ambient humidity levels. In a former publication, we have shown this concept, and but in this case not with LIG yet, but with inkjet printed electrodes, and it becomes obvious that at rather low humidity levels, the resistance of the LIG layer becomes very high. So at low humidity levels for commercial readout electronics, you can consider this more or less as open circuit at low humidity levels, which can pose issues when using this with commercial readout electronics or commercial sensing chips. So for the adapted design, which will be referred to as sensor 2 design, we introduced a conductive bridge, which can be seen as a parallel resistance to the sensor resistance of the Chitosan. And if you consider the Chitosan resistance as an exponential function, as shown before, and then consider this with the parallel circuit, then and the humidity becomes too low so that you have an open circuit here, then you can assume that the total sensor resistance is won't go beyond a certain threshold, which is the serial resistance between the electrodes and the bridge that goes across those electrodes. So this is the concept, and then the sensor design is consists only of 3 steps. So in the first step, Chitosan is drop cast onto a glass substrate. Afterwards, the electrodes are laser scribed by means using a commercial CO2 laser. And in the third step, there is a second protective layer of Chitosan applied onto the electrodes, as graphene can be quite sensitive or unstable in humid environments. Here you see on the right side a microscopy image of the LIG on Chitosan layer. The LIG formation results in a porous structure with pore sizes of around 40 to 50 micrometers in diameter. The overall sheet resistance of the Chitosan layer is 5.5 kilo ohms square. And we did Raman spectroscopy, where you see here that the 3 distinct peaks for LIG formation, the D peak, the G peak, and the 2D peak. The blue line represents the Raman spectroscopy of the pure Chitosan, and the orange line represents the LIG on Chitosan. Following this, both sensors have been characterized. Here on the left upper side, you see the sensor 1, the one without the conductive bridge across the electrode structures. And as expected, at a certain, below a certain ambient humidity level, the sensor resistance rises and can be considered as open circuit, as it's couldn't be read out using even our laboratory equipment. Below this, you see the sensor curve of the sensor 2 design, where you see that as expected, the resistance is limited to a certain threshold, and it won't rise above this. When considering the simplified equivalent circuits that have been presented before, so here just with the series resistance for sensor 1 and for sensor 2, the parallel resistance, you see that it has a very good fit to the theoretical models with R squared values of 0.9986 and 0.9993 3 for the 2 different sensor designs. Depending on the sensor design, a higher sensitivity can be achieved either in the lower or in the higher humidity range. However, below 40% relative ambient humidity, the sensors are not, it's not the operating range of the sensors. And the sensors have demonstrated good repeatability over 3 cycles, as demonstrated in this upper right graph. And also the sensors have shown to be stable over a period of 24 hours, as seen here on the lower right. So to summarize this, we've demonstrated the realization of a resistive humidity sensor made from LIG on chitosan, which poses a more sustainable approach to resistive humidity sensing by employing bio-based materials and sustainable manufacturing. By using different designs, you can obtain tunable sensor characteristics. This has been done as part of my PhD project, which is in joint collaboration between Silicon Austria Labs in Austria and the EPFL in Switzerland, under supervision of my professor, Sandro Carrara, which is also here. And yeah, if you want to contact me, please do so. Thank you very much for the attention.